welcome everyone. I hope you can hear my voice there. Let's do a quick sound check. Apparently we sound like we are in a tunnel. I hope this is a little bit better as I put my headset on. Let's wait for a little bit of feedback from our audience here. Okay, voice is okay. Thank you very much. Okay, well let's get going. Thank you for joining our second webinar from Autodesk Simulation 2017 portfolio series. Today we're going to be talking about Fusion 360 capabilities. Let me close my other programs here. Okay, and the control panel, and let's proceed. So, for those of you new in the Autodesk space, you might want to find out first what Fusion 360 is all about. We're going to do a quick check on that. Then we'll talk about what would be the differences between the current state of simulation in Inventor and what Fusion 360 brings anew. And we'll look at some of the capabilities of Fusion 360 Ultimate, and we'll try to answer some questions at the very end. So hopefully we'll cover everything in the allotted time. Well, the main question here is why bother simulate? Well, there are many answers to that, but one answer that I like and I agree with is to be able to make better decisions sooner in your design process. So traditionally we would run our model after tiring and time-consuming simplification through all sorts of tools to figure out why is it breaking, why the customers are dissatisfied, and so on. We're trying to change this workflow and introduce simulation early in the design process, provide you with the tools that will help you make sure that as you go along, as you develop your designs, you are making the proper design decisions, and you are not let's say, devolving the design as you go, but you are improving it. This is done in different ways, but ideally through a tool that will let you consider design, modeling, simulation, machining, all in the same interface. That we think would be ideal. This is what Fusion 360 wants to offer you, and it continues to be developed and enhanced over its often upgrades. So what you see here is a number of screenshots from Fusion 360 where you'd see 3D modeling, you'd see some electronics CAD, you'll see machining toolpaths, parametric solid modeling. Here are some of the capabilities of Fusion in a more detailed format. So we're talking about a complete solution from conception in terms of free-form modeling, parametric modeling, push-pull surfaces, mesh modification, solid modeling through assemblies, part libraries and content, drawings generation. That will take your model then through simulation and testing of capabilities there in terms of stress, thermal performance, assembly, and joint motion studies, all the way to actually being able to create that, validate the manufacturing process of your design through CAM, 2.5 axis, 3 axis, all the way to 5 axis machining, facilitating 3D printing by reorienting the model, visualizing printing, 3D printing envelopes, and allowing you to do all this in the context of a data management system with version management, design branching and merging, collaboration and synchronous design reviews. So Fusion 360 is a cloud-based solution in the sense that your designs are saved in the cloud. They could also be saved locally. You're able to work disconnected from the cloud up to 2 weeks, after which you'll be you need to log in again. It has a fairly small footprint on your computer, less than 2 gigabytes download, and also the ability to run some of these simulations, as you'll see, in the cloud and take advantage of the cloud computing capabilities. So a little bit different than the desktop modeling tools that you might be used with, but nevertheless a modern tool. So let me just close this window here. Beside Fusion 360, some of these capabilities are included in its extension called Fusion 360 Ultimate. Here's a screenshot of a roadmap about 3 months old now. New one, it's in the works, will be released in this month. So in terms of simulation, we're looking at existing capabilities, static stress, linear static stress, model analysis, thermal and thermal stress, cloud simulation, and there are some opportunities here to enhance the capabilities through extra functionality, like event simulation, time-based, shape optimization, Nastran solvers, as well as on the CAM space, 4 and 5 axis machining and CMM probing. So this would be available over the Fusion 360 capabilities. Those of you that are currently users of Inventor, Autodesk Inventor, are already familiar with Inventor Professional, thank you, are familiar already with some of the tools on the simulation space in stress analysis, linear static stress, model or natural frequencies analysis, shape optimization, some capabilities in terms of meshing, like tetrahedral and shell elements, linear and higher order, adaptive meshing and automatic convergence, as well as the limitations in terms of maybe a reduced possibility of post-processing, the ability to run these analyses sequentially, one by one, because we're taking advantage of local resources only. Some of these capabilities are already included in Fusion 360 and expanded. For example, mass participation factors in model analysis. But some of the tools here in terms of heat transfer and thermal stress are among the most wanted tools designers have requested along the years in Inventor. So this is an opportunity here to expand your testing, digital testing if you want, through the use of Fusion 360. Cloud solving and NASCAR solvers are also enhancing this process. Fusion 360 Ultimate will add bolt and rigid body connectors for a more efficient mesh generation, critical buckling, linear buckling, nonlinear static stress, so the ability of studying nonlinear material behavior, event simulation in terms of dynamics and time dependencies, and shape optimization. It's also a possibility there. In terms of post-processing, Fusion 360 does overcome Inventor's limitations. So here are a couple of screenshots. Beside the fact that the interface is a lot cleaner and smooth, if you want, the post-processing capabilities have been enhanced by a quick way of looking inside the model through slice planes and through the ability of plotting the volumetric mesh. You can see on the left side how by manipulating the legend simply through a matter of dragging the minimum value up, I'm hiding at that point elements that are in areas of really low stress that I maybe do not want to see at that point to enhance and isolate the higher stress areas. The ability to slice the model with planes that you can orient at will, again, it's useful to be able to verify the internal, let's say, temperature plot of a model. Another shortcoming of Inventor in terms of local solve could be overcome by using the cloud simulation, cloud solving. So the main advantage here would be the fact that you are sending these analyses to the cloud to be solved in parallel. So you're not locked down on the local resources, but you're taking advantage of a lot more computing power at that point. Once the results are downloaded back, you can start visualizing them and do all the post-processing activities that are required. If you, let's say, are running some early stage rough runs, then you could do so locally still and not take the expenditure of those 5 cloud credits per simulation, and take advantage of the cloud power, let's say, when you run the final, the more difficult, time-consuming analysis at that point. Let's look at some of the capabilities now in terms of what is different from Inventor. So as I was mentioning earlier, heat transfer was one of the most asked for capabilities in Inventor. Here it is now in Fusion 360. Currently, we're limited to steady state, but we do cover all the conduction, convection, and radiation modes. The thermal contact types are bonded with the ability of manually controlling the thermal resistance or conductance, as well as the offset bonded contact. So that's a plus there. So let's take a look at a quick short video here. You're looking at a temperature plot of, let's say, a smaller radiator, a bent pipe that runs a hot fluid, and the temperature variation along those fins. that have been introduced in the design. And here's a slice plane, the distance 50 millimeters. That will let us again see the temperature variation inside. Point probes allows us to identify at specific locations specific temperature, and surface probes will let us again select surfaces and look at the an average value there. Let's see how this is set up. We're jumping into an original model here, switching from model environment to simulation environment, and defining a thermal type analysis. Let's look at the mesh settings. Under mesh, we have the ability of specifying an average element size in either relative terms to the model size or absolute size, as well as the adaptive mesh refinement that you are familiar with for higher order elements, and a reduction of the element size based on convergence criteria. The model includes a number of components that we might not want, so we have the ability of suppressing those simply by unchecking those checkboxes. Material characteristics could be assigned here and either overwritten, or we can choose the material defined in the model. Let's look now at some of the loads. We're going to hide visibility only, right? So turn off the bulb, turn off the fins, visibility of fins, and then select all the internal surfaces, assign a temperature of 75 degrees Celsius. So those are wet surfaces in contact with hot fluid that we assign a applied temperature boundary condition. This process is usually bottom or top to bottom in the browser, left to right in the ribbon, pretty straightforward. Here are the other load types. Fins will dissipate heat in the surrounding air in the room. We're assigning there a convection coefficient that could be constant or temperature dependent. In this case, let's make that constant at 5e minus 6 watts per square millimeter Celsius. That heat it gets dissipated in ambient temperature of 20 Celsius. As well as main heat dissipation mode here, radiation. So we're selecting the surfaces of the fins minus the surfaces in contact with the hot pipe. So we're subtracting those, and we're assigning a radiation boundary condition. Automatic contacts will ensure that these parts are touching. If the contact there has no input in the thermal resistance, that means it's a perfect contact, no resistance there. We're running this and locally, and here is the outcome. You can see the pipe at 75 Celsius there. Let's stop this for a second. So 75 degrees Celsius on the pipe, dropping down to around 73 on the fins, based on the assigned conditions. Pretty straightforward setup and a quick run on a simple model. Let's look at thermal stress now. So this would take the results from a thermal analysis in terms of strains due to expansion and contraction, and use those as additional loads in a static stress. And we have the ability of assigning all the contacts from the linear static stress material as well as the thermal contacts, and add the additional boundary conditions, loads, pressure forces that we already have in the static stress. So what we have here is a 1/8 model of a rotor. The temperature assigned there was 400 Fahrenheit, and we're looking at results in terms of stresses as well. How is this done? Well, again, in a new model, I'm switching to model space or model environment, going to simulation environment to load the model in. There's no translation. Everything happens in the same interface. Assign units and materials. The Autodesk material library is something I'm sure you recognize here. Assign constraints. So again, it's a 1/8 symmetric model. So we're assigning symmetry boundary conditions on the newly created faces there. So symmetry by y-axis, and then symmetry by x-axis on those fins. Okay. Actually by z-axis in that orientation. Yeah. All right. Then in terms of loads, as I said, access to both structure and thermal loads. So let's say a applied temperature at the hub of 100 degrees Fahrenheit, and a applied temperature due to friction with brake pads at 400 Fahrenheit on the rotor face. In terms of analysis settings, we are looking at, again, the mesh settings here. Let's say model-based mesh, as percentage of the model size, running the analysis, and downloading the results will let us look now at a safety factor of around just 1.1 at its minimum. So based on the boundary conditions, structural boundary conditions, and the fact that we have applied a heat source and material expands, we're looking at stresses due to that thermal expansion and an equivalent safety factor based on yield strength. And something similar in terms of a larger assembly. As I said earlier, Fusion 360, it's a hybrid modeler if you want. You can bring in components from other systems in terms of being able to translate them, modifying them through press-pull type modifications, or design them parametrically from the get-go. Here's the isolation of that brake pad and the ability to use that in the simulation environment. Assign again a set of thermal boundary conditions, this time as surface heat, and run the analysis with the default mesh settings. It's something you can always go back and refine. Here's the temperature plot, the resultant temperature plot there, and the study then gets copied and switched to thermal stress. So the previous results are available as loads in the new study. The location of those bolts it's going to be under a pin constraint. Okay, and here's the result here. safety factor and displacement values, safety factor below 1, higher stresses, so this requires a design change. There's the ability of hiding low stress areas, and now by applying an extra load, let's say the moment due to the application of brake pads, we have maybe a more accurate picture of what actually happens there. And obviously, with extra load, the safety factor drops even further. So this requires a geometric change, and this is what is going to happen here by isolation of this brake rotor and modification of the number of fins. We're again back into the simulation environment and simply rerun the analysis after making sure the boundary conditions are in the same locations there. And here's the result on the redesigned brake model. So as you can see, this can be done back and forth, switching between model and simulation environment with a minimum effort. And that allows you to quickly validate the designs and make sure you're on the right track. Okay, let's look at another situation here where, again, from part of the capabilities of the tool, structural buckling. In terms of inventor capabilities, you probably remember the design accelerators. It has a linear or critical buckling ability on single member only, so fairly limited. That's not the case with Fusion 360 and structural buckling, so we can do that linear buckling analysis in terms of eigenvalue modes and look at the buckling coefficients in terms of those results. So this is, again, pretty easy to set up. It's a matter of switching again from model to simulation, setting up a new study, structural buckling type. Okay, so again, we're talking ideal buckling. Okay. How many modes we want to run this for? 3 is default. If you're looking at a let's say a more accurate buckling situation where, let's say a nonlinear type situation, you might want to take this farther through an event simulation type analysis. So this is right now linear buckling. Okay, or setting up boundary conditions there, so fixed surfaces on the bottom, applying a load on the top of, say, 1. The buckling coefficient will allow us to multiply the load and get an indication of what the value of that load where the linear buckling will occur. And again, it's not a conservative estimation, right? So you have to remember this is ideal buckling type analysis. Okay, so once the analysis results come back, get downloaded from the cloud, this is something that you will have to wait for. You have the ability of looking at the 3 requested buckling modes here. Okay, so this plastic table will buckle under 171 pounds in its first buckling mode. Next, event simulation. So this is where things get quite interesting in terms of expanding the capabilities of of the tool, we can now look at time dependencies of capture the behavior of that structure, look at large strains, large displacements, breaking of the part through element deletion, and in terms of computational expanse. But this is actually very small because it's using not an implicit but an explicit solver. So here's a situation where we're after the behavior of, let's say, trying to snap these two plastic parts together. What's going to happen with the stresses, what values are going to occur, well, these stresses are going to occur in the plastic components. So from a setup standpoint, it is pretty straightforward. Once we go to the event simulation type analysis and assign the proper materials, we will have now the ability of assigning some prescribed displacements or velocities or accelerations. So right now we're just saying these two parts can only move along z-axis, and the prescribed displacement of part on the left, the vertical one, is 11 millimeters in the negative direction of the z-axis. The analysis is going to run on a really short time interval, 5 milliseconds, and we can do the same for the part on the right, plus 11 millimeters in the same time interval. So this curve multiplier lets us vary the load with time in a quite precise mode. We're adding gravity as the only type of load, and we're running the analysis, the total event duration here, okay, for this interval, setting up the mesh, and solving the problem. Okay, so you need to remember the time interval. You want that to be smaller than the curve time defined there. And here are the results. And here's a variation of the stress along that set of iterations. Here's a bit more funnier example here. An axe going through a number of plywood or plastic boards. You can see how by specifying an initial acceleration, we actually don't need to start the analysis all the way up, high up above the part impacted. And you get to see the transient result plots, which will show us the variation of the stresses on the involved components here. On a more serious note, there's a more real application where we can have a say a die draw type manufacturing process where, let's say, a copper billet is drawn through a die. This is the die is defined as a rigid body, so infinitely stiff, and by specifying a certain prescribed velocity on the copper billet, we're getting to look at the variation of stresses, and you can see how the maximum stress is around the yield value there once the material goes plastic, and the final result, the final shape of the component. So you can see how event simulation could be used for multiple applications in terms of nonlinear materials, time dependency of loads, and the solution tends to solve rather quickly. Okay. Okay, let's look now at shape optimization. And again, Inventor users might be familiar with this just because it is a current capability of the Inventor, where what we're trying to do is identify in an assembly the actual load path applied to a part, and then take that part and approximate it with a much lighter one by removing material, and basically redesign the component to reduce its mass. So what you see here on the top right side is a plot of so-called path criticality. Basically, in terms of defined boundary conditions, loads and constraints, and how we're applying the so-called regions to keep, so areas where material cannot be removed from. The software will propose a new shape of your part. That shape is in a mesh type model, but Fusion is quite flexible here, so we can easily model that finite part around it. So we're creating a much lighter part by specifying the target mass reduction and maximizing its stiffness. Let's look at an example here. So we're trying to end up with a part that is closer to this shape, starting from this shape. Okay, so again, back into simulation mode. The study type is going to be shape optimization. And in terms of constraints, we're going to, let's say, pin the two cylindrical faces there. And we're applying a load on the flat face on the opposite end of the gripper. Okay, so let's say 500 newtons here. Shape optimization allows us, as I said, to define areas that we want to preserve. So there will be, in general, areas where this part contacts with others which are not included in the shape optimization type analysis. And these volumes where these are the volumes where material it's not going to be removed from. We're defining a symmetry plane as well. And once we run this, based on specified criteria, which are target mass less than 40% and maximize the stiffness. Again, here the mesh the definition here on a fine mesh. Okay, so we're running this on the cloud, and after data is received and the file is saved, we're looking at the result. So let's pause this for a second. So areas in this volume, or areas in the center where say the material is not loaded, going to all those elements in those areas are going to be removed, and areas which are critical for the proper functioning of this in terms of enhancing the strength, maximizing the stiffness, are going to be preserved and painted in red here. So this is the final result here. Okay, well that's all for today. A couple of things that I wanted to point out. As I always like to say, don't struggle alone. Here are some of the resources that you can always go back to. simhub.autodesk.com is the Autodesk portal for simulation. There are plenty of forums for different simulation products. Ask your questions, and hopefully you'll get your answers. And generically speaking, the Autodesk simulation portfolio is rather vast. We are in various spaces in terms of plastic modeling, advanced materials, the ability of deal with complex designs, and that's about it. I hope you enjoy this. Let's see if there are any questions. Robert?
Just looking through, everybody's good. If anybody does have any questions, you can always reach out to us. Specifically, you can reach out to me. I believe my email was in the initial contact information, or you can just actually support@solidcad.ca and someone will be able to answer that. So thank you again for attending. As we mentioned before, we will run a simulation type event once a quarter. This was the first of the year, so look out for our next one in a couple of months, where we're going to focus on some of the highlights of Autodesk CFD. So look out for our invites. Looking forward to having you. Thank you again. Take care for now.